Okay, this is the OLLI course, Energy and Economics, Biophysical Approach, and presented by myself, Charles Hall. And just for a second, I'm going to see, does anybody have any questions they want to ask me at this time? Okay. Rob, would you turn your microphone off in case there's any feedback? Thank you. Okay. I don't know if we have fewer people than we used to or what, but I'm going to start. All right. This lecture is going to look at the concept of peak oil or concepts of peak oil, energy return on investment, and limits to growth. These are three issues that have been important to me. And they're important to me because I think they're important to the world. As the last lecture talked about the importance of industrialization, which means basically the burning of fossil fuels, but we have to include water power and nuclear and increasingly solar. And wind is solar as well. It's due to the unequal heating of the earth, which causes some areas for the air masses to rise and create low pressure and air masses from elsewhere to move there. And the result is what we call wind. And we talked about how important wind was, incidentally, in earlier European exploration and so forth. But let's take a look at non-renewable resources for a while, the pattern of use over time. And this impacted me because I was one day browsing in the University of North Carolina bookstore, which as a graduate student I would frequent, and found this. And back in the pre-politically correct days, Resources in Man, Resources in People, which was set up by the National Academy of Sciences and the National Research Council, which in the past, and I think not as much now, or at least I don't hear about it as much, would take issues of scientific importance to humans and would look at them gather a bunch of different scientists, and I've done this a few times, and discuss these issues. And in that was a chapter by this guy, M. King Hubbert, who I actually knew fairly well. But this was quite amazing to me. At that time, I was interested in ecology, and not ecology of humans, ecology of natural systems and fish, and didn't pay very much attention, although with Earth Day and all, of course, we were paying more attention to the general media attention to ecology, which was beginning. And I just want to make sure that there's a difference between ecology, which is the logos, comes from the Latin or Greek logos, which is study of, and the study of eco, interestingly, is the source for both economics and ecology, and it was considered the household. So there's a broader out household, which is ecology, and the more explicit household, which is your personal finances. So, but I was very much attracted to the scientific methodology of this guy. And he came up with the concept, although he didn't use the term, peak oil. And let's start here. Depletion, we understood about depletion, but what is it really? As every beer drinker knows, the glass starts full and ends empty. The quicker you drink it, the sooner it is gone. The same principle applies to oil and gas. How has this self-evident reality, been concealed from the public? Has no clue. I was interviewed by somebody who did some podcast called $1 Million Books, and they chose one of my books for that. And he had no clue. He had no clue about oil depletion. It is so obvious that it is a devastating realization. So, all economic growth encourages the depletion of oil. And this is called Hubbert's pimple. This is within human history, recent human history. And this was the recent, and he did this back in 1950 something. So we moved this zero a little bit further along. We're living in this epoch of fossil fuel exploitation, which we think is normal. And it's completely abnormal in human history. And we take it to be normal, but it's not. Somebody please turn off your microphone, please. Thank you. Okay, and he came up with this diagram for the United States, or actually the lower 48. Excuse me, let me just take a look. And somebody had Ilya. Yeah, thank you. I guess that's good. And here's his original graph for the United States, which he made in 1955. 1955. And he said, this has been the growth of oil in the United States, rather amazingly. And I'm born here in 1943. And he said, it's going to go through something like a normal curve. And it has no relation to statistical normal curve. It's just a similar bell-shaped curve. It starts slow, and then it increases exponentially as more and more uses for, he said, a resource in general, for example, oil, is found. And then we'll reach a peak and then begin the decline into the future. He thought of this for the United States. And you might say, well, the United States is producing more oil than ever now, and that's true. But this was for conventional oil, and I've added a bunch of slides to look at what shale oil versus conventional oil means. So I looked at this graph and I said, oh my God, I'm going to be alive. Well, here I am. I'm going to be alive when this takes place. I think it's going to affect me a whole lot. So I paid a lot of attention. And he also made a curve for the world, and he didn't know whether it might peak in 1990 or 2000, depending. This Q infinity is the total amount of oil that will be ever extracted from the ground. Now, I'm going to talk about what that means shortly. And he did some, basic calculus and figuring these things out, and drew some graphs. He was mostly graphically oriented. Now, one thing that has happened for sure, this is from Gail Terberg, is that the rate of increase has enormously decreased. Probably most of you are old enough to remember the oil crisis of the 1980s, 70s, and 80s. And but basically, world oil production has ceased to increase. We haven't gone down the other side, or maybe we have, not very much yet, but certainly the rate of increase has decreased. The U.S. production, the U.S. consumption had become much larger than the oil production. And this was an old graph. I probably shouldn't even show it now, but we'll talk about it a little bit. Now, the economists did not like Hubbard's concepts. They thought any resource scarcity would be compensated by lower use, by technology and substitution. So there was no reason to worry about it. And we're going to talk about this some more, but there was a paper by Barnett and Morse who supported that perspective. So let's take a look at Hubbard's original prediction for the lower 48, which are these yellow triangles, and actual oil production in the United States. Well, it peaked, as he said, in 1970, and it has declined. This is for the lower 48, almost the same as Hubbard's prediction, at least into 2007. Now, Hubbard said, I heard rumors there might be oil in Alaska, but there's no data, no information, so I'm not going to worry about it. And so if you add in total production in the United States, including Alaska, you can see Alaska made a big difference, but it wasn't enough to bring the peak up again. Okay, so that's where we were in 2007. And Alaska, incidentally, was very important, but that too has been declining. And this is versus cumulative production, the annual production, and we're down here somewhere. Prudhoe Bay is the largest oil field we ever found, and it's all essentially gone. So let's look at, people asked me last week about shale oil, so I put in quite a bit more in this lecture about oil, and this is the conventional way of looking at oil, how we get oil. And the idea is that you drill down about 2 miles, and there will be a trap. A trap means rocks that are impermeable either to water or to oil. There are certain kinds of sandstones, for example, that oil just won't go through. And we'll talk a little more about that in a minute. And because of density, the gas will be at the top, the oil will be next, and the water will be at the bottom. And what you want to do is, you're thinking of seeing oil spurt out the top of an oil well, and that can happen, but an oilman doesn't like to see that, because you're wasting the gas, because the gas can push the oil up the pipe. And that's an important thing. Getting the oil up the pipe is not an easy factor. And as you extract the oil, the gas expands, the remaining gas expands, and the pressure decreases, making it harder. So a great deal of what you do in an oil field, you're used to seeing these grasshoppers, but this is less visible, but it's there, and it's using a great deal of energy, is you're pushing gas or water, sometimes CO2. Natural gas is the best stuff, to push the oil through the formation. Now, the oil in the ground isn't like oil in a can that you pour into your engine. It's in little droplets that are interspersed. It's like an oil-soaked brick, really. And you got to push the oil through these holes, through these interstices. And we usually get only about 30 to 40% of the oil in an oil field, because the oil field is only partly, the word they use is permeable. Porosity is how much space there is between the particles, and permeable is how easily you can push stuff through it. So you have a collection well with a familiar grasshopper here, and getting gas as well from here if gas comes up with the oil, which is usually re-injected, by the way. But you only get about 30, 40%, leaving 2/3 of it behind. Now, there's a new technology that's of interest to me. We can probably increase this a little bit additionally using bacteria, but that's another story. But if anybody interested in that, I can talk about it. Now, another thing that was not emphasized as much, even in the oil field, although a good oilman, of course, would know this, is that there are two types of rock that have oil in it. One is what's called the source rocks. And this is an old anaerobic basin in which the oil was formed. But the oil, being light, will work its way up through the formation, if it's permeable, until it gets captured by a trigger. And then that's where it'll stay. So this is permeable formation, and the brown is impermeable. And here's four kinds actually of traps. This is where traditionally we've gotten gas and oil. And fracking, which I'm about to talk about, goes principally into source rocks, where the oil is much less concentrated, but there's more of them. So you look at this and you think, wow, these are all source rock areas in the United States. And here is the Bakken is an important one. Right now, the Permian in Texas and New Mexico is really important. Barnett was originally important, but that's essentially exhausted now in a matter of 10 years. And a lot of gas comes from Pennsylvania and the Appalachian area in what's called the Marcellus Shale. We don't hear too much about these other areas, but there is some source rocks there. They even have a little bit down here in California, and I don't think they've got a bit out of it. Actually, good shale rocks are rare in the earth, and I'll give you an idea of this. Here's Texas, and Texas and the Eagle Ford. I'm sorry, I didn't mention this. This is a very important area for shale oil and gas. And in this area, you get only gas, what's called dry gas. And here you get wet gas, meaning it's got some intermediate weight, butane and so forth, hydrocarbons in it. And then when you get up a little further north, it's all oil. And why is this? And it has to do with the geological history. This is very well cooked oil. If you cook oil enough, you crack it. That's what it's called, cracking, cracking, into natural gas. So here we have oil, here we have oil and gas, and here we have gas from the wells. And this also takes place elsewhere. Some other geological movements have put traditional oil along up here in, it's called the Austin Chalk. Now, when I started studying this back in 2010, I noticed something that most of the large oil fields, the size of this is oil and this is gas. Most of the large oil fields were concentrated. These are all the wells that had been drilled as of 2010, and this is amazing because they developed the procedure in 2007. In 3 years, they'd already made this many wells up in North Dakota. And here over in Montana, there were some, in a place called Elm Coulee, which had once been traditional oil fields. And I showed you some pictures. Parsol is about here. I showed you some pictures driving through here. But they're concentrated. And what the oilman calls them is sweet spots. And you get an idea of what a sweet spot is. This is near Fort Worth, Texas. And as far as you can see, more or less, over here is Fort Worth, Texas. You have every half mile, you have an oil field or gas field, and they're going down. The idea, the guy who invented this, and I meant to, not Dad Joyner, it's somebody else. His daughter was sipping a soda with a flexible straw that had a 90-degree bend in it. And that gave him the idea of doing what's called horizontal drilling. And what they do is I had a picture here. No? What they do is they drill vertically 2 miles, and then they can turn the drill and drill horizontally for 2 miles, and they follow the oil. The oil might go up and down with geological structures, and they analyze the cuttings as they come up, and they can direct their drill. It's just amazing technology. And what happened was, in about 2006, the average oil field was only about 50,000 barrels. Which is a damn small oil field. And it was looking pretty bleak for the US oil industry. And the important thing about the oil field, or one of the important things, is these wells give you about 700,000 barrels apiece. They don't last at high rates for very long, but they give a lot of oil in the first 2 or 3 years. So you go down 2 miles, go laterally 2 miles, you shoot explosives to crack the rock, and you put in water under tremendous pressure to crack them further, and then you suck the oil out. And that has, I'm an environmentalist, I'm an ecologist, I hear all kinds of stuff about how bad oil is, but let me tell you, that saved our ass. Because without that, Russia could do anything they wanted to us now, because they've got a lot more oil than we do, except for the fracking. And so the production of oil, which had peaked in 1970, had declined to 2008 or 9. And then this the oil shale kicked in. This is 2017, where there was, I can't remember what happened, a financial jigger, I guess. This is COVID, and it is now leveled off about here. So, in fact, we can look it up today at the end of the talk. We can, if anybody wants to see whether it is still flat. Okay, now I already had some experience with oil. And I wrote this paper, you can see up here, 1981. petroleum drilling and production in the United States, yield per effort and net energy analysis. So that was looking at how over time in the United States, the production of oil, the efficiency of production had declined because you got less and less, just like for fish. Very classically in fisheries, the more you fish, the less you get per effort, per boat day in fisheries. And so the more you drill, the less you get per foot. And we did a net energy analysis of that, which was, in other words, energy return on investment, which was declining. So I had some notoriety. This is a good place to publish, very good place to publish. So I had a bit of a notoriety in that field. So about 2001, I decided I needed to learn more. I hadn't done too much on it. I'd just done ecology, tropical ecology for 20 years. So I decided I needed to learn more. These guys, Larare and Colin Campbell, wrote a really good paper out of nowhere for me, The End of Cheap Oil. So I went to talk with this guy, Jean Larare, who knew more about how much oil was left than anybody in the world. I was really impressed with his work. And he had been chief of exploration for the French giant oil company, Total. And he had this beautiful, beautiful farm that had belonged to his family. And up there, I decided was the only place in the world where there was reliable information on how much oil remained. It was amazing. And I still think that's essentially true. That this guy, and only this guy, is keeping accurate records. And I further looked into this a lot more, and I can tell you the initial estimates of how much oil there are criminally incorrect. Now, in general, what I found back then, and is still true, this is how much oil we found by decade over time. We found a lot of oil in end of the 1940s, Saudi Arabia and so forth, found a lot of oil. In the 60s, 50s and 60s, but the amount of oil we found each year, that's gigabarrels per annum, that's 10 to the 9th barrels per year, and this is how much we used. So the difference between how much we used and how much we discovered, production is the same as use because we use it immediately. This had to come out of here. In other words, little calculus for you. The area under this gray curve is how much oil we found. The area under the black curve is how much we use. And for those years, and this is continued out now to 2023, we use a lot more oil than we find. And so that means we're just using up this oil that we found in the past. We're pumping out the old oil fields. And about half of our oils comes from big fields in the world. 400 big oil fields are more important than all the little ones, and the fracking might not quite fit into that category. Okay, and what I learned from John is the official data is very unreliable. They meaning those who maintain the official oil statistics, Energy Information Agency and British Petroleum and other official keepers of our oil reserves, they ask political entities for reserves. They don't do it in any scientific manner. They do it by asking nations, which often give them what I should call political estimates. Revisions and additions, this is trickier. Most oil we find in a given year comes from revisions and extensions of old oil fields, and they were treated as if they were new oil. So it looks like we're finding more new oil than we are, but in fact, we found the oil field a long time ago. And sometimes a large oil field which supply half the oil will suddenly crash, as happened with Cantarell. This is the second largest oil field in the world in Mexico, which just crashed about 8 years ago. So I guess 12 years ago by now. So this makes it a little nerve-wracking. Another thing I learned is something called Hubbard linearization. If you plot, it's a mathematical technique, the annual production over the cumulative production versus the cumulative production, and this is the same as time, over time. Now Pennsylvania anthracite, no, there's zero coal being mined. So it's a resource that's been totally depleted. You see, we could have predicted this through this process. It's a straight line. We could have predicted it back in 1920 or something. So I got very fascinated with this mathematical technique for prediction. I still don't quite understand how it happens, how it works, but it does. But in the official estimates of reserves are going up and up, but the Hubbard linearization says for oil, which I will show you, you don't have that much left. So here's the official estimates of remaining oil reserves that increase year after year. But we published this paper, How Much Oil Remains for the World to Produce, and we compare assessment methods and separate fact from fiction, at least we hope we do. And we find that, in fact, done properly, the production of the finding of new oil, this green line, has gone almost to zero, and our consumption still is very high. And we compare our method, the green, with the official method, which is the red. And the reason is that we attribute the revisions and extensions to the year that oil was found, that field was found. And they put the revisions and extensions. People must be out there saying, well, what the hell difference does it make? It makes a huge difference in whether our reserves are still increasing or, as I believe is accurate, our oil reserves are declining, so that we have only about half the maximum we ever have of oil left in the ground, even though we keep finding a little bit. So if anybody wants, I'll send you this paper and you can go through all of the procedures we went through and the math and all that stuff. But the point is, the official estimates are too high by about a factor of 2, which means that we will run more or less completely out of oil a lot sooner than anybody thinks. And here's Hubbard linearization. Look at COVID. COVID made a big difference, that last blue dot. But the Hubbard linearization, this is different categories of oil. This is what normally is called oil, just plain oil. And we've used about 1,500 megabarrels, and in other words, about nearly two-thirds of the 2,500 we expect to get to get ultimately when we're all drained the last oil mill. Okay, Carl Vischer. Okay, let's view. Carl, you have a question? Hello?
Carl, you're muted. Carl, you're muted.
Or your mic is dead.
Oh, you have a question? Maybe his cat stepped on his keyboard. Okay, we'll take questions at the end, but anybody have a burning question, I'll answer it anytime.
I have a question.
Yeah,
Yeah, so what takes up the space when the oil is removed? And how does that affect the geology of the Earth's crust?
I'm sorry, would you say that first part of that again?
When the oil is removed, what takes up the space? Air?
The earth sinks. And because it's 2 miles underground and there's an awful lot of rock in between, normally it doesn't make a lot of difference except once in a while where it does. In the Netherlands, for example, where they've taken out a huge amount of gas, that's become a very important issue, environmental issue, and even though they have one of the largest gas fields in the world, the Hoveningen, I probably didn't pronounce that right, field, um, they've stopped taking out the gas because entire communities are unevenly sinking into the ground. And that has happened in a few other places, but that's probably the most notable place. Okay?
Thank you.
All right, let's go back. Um, Wait a minute. There. Okay, but the Hubbard linearization, which we think is a pretty good tool, indicates that we're going to be running out of conventional oil very soon, but there's other kinds of oil. And if you correct for the fracked oil, you go from 2,500 to 3,000 gigabarrels. And if you correct for this is really hard to say whether we're going to do it, but even if you include all of the really nasty, heavy stuff in Canada and in Venezuela, what's called heavy oil or tar sands, you might be able to add another 1,000, and we'll show you the implications of this. And if you include natural gas liquids, meaning the butane and the pentane, the very, very light oil, it's really gas, that you got from natural gas, we can extend it a little longer. And we'll take a look at what this means. But don't forget, this is the stuff of which we've used about 2/3, 1,500, there's a few more years in here, versus 2,500. That's the stuff civilization is based on. Now, we make a projection into the future, and we did it just at the time of COVID. So COVID added an interesting quirk to this. So this purple line is our estimate of the future of conventional oil. And you can see it's declining. That decline started in 2018, a couple of years before COVID. And it does seem that we've reached the maximum. COVID added this strong dip right here, and we bounced back a little bit, but not all of the way. So this is conventional oil. You're not going to run out. It's just going to be less every year. This is conventional oil plus fracked oil. Estimate for the whole world, most of it in the United States. This includes Canada tar sands. You see, you're only moving the peak up to 2040 at most, even with all of these non-oil categories thrown in. And then you add natural gas liquids and biofuels in the kitchen sink. Everything you can think of, you can push it out here. So natural gas and natural gas liquids are inevitably going to become very important, and they'll probably keep civilization humming along for a little bit longer. So the question is, can we take whatever surplus is left and transform that into wind turbines, solar PV collectors, and so forth? I've got 31 panels on my roof, and I won't live long enough to see my money back, I don't think. Somebody will. So it's looking at the future is either very simple, which is, hey, we have reached peak oil, we're on our way down, or more complicated, because then you're going to say, well, we might squeeze out a little more from fracking, and we might squeeze out a little bit more from tar sands, with horrible environmental consequences. And we might start burning more and more propane in our cars, or whatever we're going to do. So that's our best guess, and it's a pretty good one, I think, of what the future of petroleum will be. But certainly we do not have even another generation of anything like expansion based on any petroleum fluid that we can come up with. And this is just comparing our estimates with some other ones that we thought were pretty good. World Economic, World is oil in there somewhere. I can't remember exactly. Here are predictions compared with certain other people, and they're not so terribly different. But they're not the official ones. These are other people whose estimates we think are good. So that's, where is the oil remaining? Here's a good way to look at it. Who has the oil? And the United States should be a little bit bigger, and Canada perhaps a little bigger if you include the crummy oil. The shale oil, well, that's not crummy oil, but it will be soon. And the Middle East has most of the oil. Iran, Iraq, Saudi Arabia, they're big players. So that's going to be politically enormously important in the future. Venezuela doesn't have so much regular oil left anymore, but they have a lot of very heavy oil. So will the world produce that or not? I don't know. Anyway, here's a guy I like, Matt Mushalek from Australia. We can look at peak oil this way. Peak oil for most regions of the earth, from Asia, Mexico, Europe, South and Central America, Africa, US conventional oil, all of these have peaked and are declining, just like Hubbard said. Even Russia, perhaps. Saudi Arabia, no, they're still increasing. And as well as other places in the Middle East have a bit of an increase. And here's US tight oil up here, which even on a global perspective has made a difference. So has the world peaked or not? Well, looks like approximately. But, and I don't see anything else on the horizon that would change it. But what has really happened is that for particular countries, for conventional oil, this is conventional oil only. We did a very big study back in 2004. Let's look at Yemen. And we made predictions if there were low estimates, medium estimates, or high estimates made by the United States Geological Survey, how much oil we thought would be produced over time. And we made these predictions of low reserves, middle reserves, and high reserves. And for essentially 38 of 45 oil producing countries, they've reached a peak and have declined. So that peak oil is a reality for most oil producing countries, but not yet for the very largest ones, including those in the Middle East. And the happy accident for us of fracking in the United States. Incidentally, most other countries do not have good rocks for the kind of fracking that we do in the US. So it's unlikely to make much of a difference. Argentina, it's made a little difference, but not too much. Another thing that we found, this is my own research, is that this is the production of oil. Let's see if we can get this from 1950 to 2010. This was older work I did. This is the production of oil, and this is the drilling that we did. And you hear Trump say, for example, other politicians say, drill, drill, drill. But when in the past we drilled more, we didn't get more oil. We just produced it less efficiently. It's just like fishing. There's only so many fish to be caught, only so much new oil to be found. So there's no indication that we can get more oil by drilling more. We just have to keep drilling at the same rate and do so intelligently and not. The price of oil went way up in the 1970s and people drilled a lot more, but they didn't find any more oil, didn't produce any more oil. Now let's go back to my PhD work in New Hope Creek. There I am catching fish going up and down. Remember, again, doing energy return on investment for migrating fish. And migrating salmon too. So energy return on investment, that's my minor claim to fame, is the energy delivered to society or to an entity, and would be to fish, a group of fish, over the energy put into that activity. And it's usually considered energy invested from society. Now I'm going to be interviewed by Nate Hagens tomorrow, and I'm probably going to talk about that in some detail. I'll make that available to you when it's available to me. And so going back to our earlier work, what we found that is the yield for foot declined while the energy needed to drill a foot increased. And at some point, we thought they would cross. Now, what a mistake we made in 1981 was these lines should not have been linear. They were exponentially decreasing. But now the energy costs of and this is one of my what's his name? Truman Capote said everybody has their 1 minute of fame or 5 minutes of fame. And mine was I was on the first page of the Wall Street Journal in 1981. This was it got us a lot of attention for a little while. Now, this is just another example of what's called the best first principle. Humans always exploit the best resources first. They look around, they find the best resources, and that's what they use. In economics, this David Ricardo has discovered this concept, and he talked about farmland in that perspective. So in the United States, this is the size of oil fields over time. We found this before fracking, we found the big oil fields first. Yeah, I mean, you almost couldn't help it. You blundered into them. They're so big. But now they're gone, long gone. And this is how we have to get oil now. That's obviously a very, very energy intensive process. Looks like they got solar collectors on the roof while they use this enormous amount of energy to make this steel platform and to get it out in the Gulf of Mexico, way out in the Gulf of Mexico, and then do very complicated drilling. So let's take a look at Norway. The only large oil fields we found since about 1970 has been Norway in the United Kingdom. And so I did a study on the Norwegian gas and oil with Lena. I can't remember her last name. Anyway, this is how much oil was found. What you see increased throughout the 1980s and 1990s, and then peaked, and has gone down, and it's over here somewhere now. I'm not sure exactly where. And this is gas, and this is natural gas liquids, which are useful materials, useful fuels. So this is the production over time, peaked, as Hubbard said, and declined. And the total, this is gas here, of oil plus gas plus natural gas liquids, peaked and then declined. And this is the energy cost over time. This is the natural gas used for production, the diesel used for production, the fuel used for drilling, and the embodied energy. That means the energy found in the structures, this stuff. That has no chemical energy. You can't burn it, or the steel, but it has a lot of embodied energy. That is energy that was used to make it. So you can see that around a third of the energy used is in the structures. And this is the energy return on oil for Norway, which this is just oil, the orange, and it has declined by half in only a decade. So let's get the years here. So from a peak in about 1995 to 2007, in only 10 years, it went from 40 to 1 to 20 to 1. And including the gas, it went from 60 to 1 down to 40 to 1. And now it's down here. This has continued. So news of these studies got around. Just a moment in my life, one of my most interesting moments was this is the Parliament in England. And here I am speaking in Parliament in that building over here somewhere. And here's some British Prime Minister, not a Prime Minister, I'm sorry, a member of the House of Commons. I guess it was the House of Commons. And I'm trying, I look smug there, but I hope I was just. But anyway, they brought in some of the very best British energy experts, and they have a lot, and that's Skrabowski, Don Skrabowski, and I'm giving my talk there, and there are these, and here's England. Here's the production of oil in England and our prediction of its decline that is made where this white line was. And we published it back then. And this is what it actually did. Our models, we can model the production of oil pretty well for most countries. Not all of them, but as I said, something like 38 or 40, 45 of them, we can model them. We did model them very well. And so the red line, the red dots are the data, and the purple is our prediction. The most important oil fields in England, that's their Hubbard. This is just their production over time, which you can see is basically a Hubbard curve going to zero. Here's another, this one is the 40s. The previous one was I can't get there. Brent, this is the biggest oil field. So they've exhausted their biggest ones. over here, I guess the yellow one was Brent. Oh no, this one I guess is Brent, and that's probably the 40s. And that's where we were in 2010. Production for more and more small oil fields after the big ones have been depleted. Hey, the point is, oil is being used up all around the world. And so we did some, let's see, I want to get to EROI. There it is. The energy return on investment for oil alone or for oil and gas. For England, I presented this at the English Parliament, and in fact, that pattern has continued. So energy return, all of our energy is becoming more expensive, and what that means, I mean, more energy intensive to get. The energy return on investment is falling, and since all economic products are made from oil or using oil and gas, essentially all, the average person will see that as inflation. And that's your take-home message. Inflation is inevitable. It's due to the physical nature of the earth. People will blame politicians, but the politicians cannot make it not happen. And what I worry about is that will make all countries increasingly difficult to govern, and it's already happening. You see it in the news all of the time, Ecuador and Argentina and France and all around the world, England. People are rioting when the prices go up, and they think it's a failure of government. It's the inevitable consequence of declining energy return on investment, because we have to use more and more of the profits of the oil industry to get the oil to run the rest of society. Oh, here we have apparently official energy return on investment that I present. What was that? Same thing. I don't know. Okay. And it's happening all around the world for different, this is Norway, this is Mexico, this is US, had a peak in around 1970 and has declined. Probably the fracking has leveled that off a little bit, but it's happening all around the world. And meanwhile, all of the metals are declining in quality. This is the ore grade over time from 1850 to today. You see, what's this one? The copper has declined from 25% down to 0.4% today, requiring more and more of our energy to grind things up. Inflation is inevitable. And of course, there are the environmental impacts. This is the oil, and the Venice oil field is a circle here. The mouth of the Mississippi River, this was once all productive marshlands. It's all been destroyed by the oil industry and going after the oil in Louisiana, and by sea level rise occurring by climate change. So I haven't even included in the denominator the environmental impact, which is huge. So declining energy return on investment will strongly influence net economic growth, costs of government, in other words, school bus fuel, ability to pay back international debts, ability of conventional economic models to work, and the value of pensions. We've lived through people of my age, I'm 80, have lived through a remarkable period of increasing energy supplies, which is coming to an end. And so this will change the world a great deal. It doesn't have to be bad if we don't understand it and manage it. But if we think we can continue growing, economically growing, when our fuel supply supply is declining. That's just not possible. All right, it's noon. I think I will stop here unless it makes sense to go on. Let me stop and see if there are some questions. Let's do that because here's Clark. Now, hang on, Clark. I've got to find my way through here. Just a minute. Can I? Here we go. Yes, Clark. Where's Clark?
Right
Hi,
here.
Clark.
Hi.
Yep.
So just a question about the revisions that have caused some folks to raise the estimate of remaining oil. So I was thinking, oh, that may have had a lot to do with fracking, but then you said that, well, fracking is really mostly in the U.S. It's not a worldwide. So what is the main, or is there a main cause, or to these revisions? Because with those revisions, there's quite a difference between your estimate and what some people estimate.
Absolutely. And I think that's a really good question, Clark. And there are two main reasons why our estimates are much lower than the official ones. And it starts this way. Let's call them the BP, British Petroleum estimates, or the US EIA, Energy Information Agency. Those are the official US estimates and for the world. And not even the United States Geological Survey, which I had more faith in. But anyway, here's what they do. They call up the official oil minister for each country. Now, in some cases, like in England, this is a good oil geologist. And you have a pretty good sense that the numbers they're giving are good. Because you've got this much oil, and every year you discover some more, so you put it in the tank, but you also take oil out of the tank. You use it. So you got to correct for each year. But the numbers for Saudi Arabia, for example, have not changed for 30 years. It's as if they used exactly as much oil every year as they produced. And that's ridiculous. I mean, most of their oil comes out of the Gawar field, the biggest field in the world, which is down in 2 miles under the ground. It's shaped like a tunnel. It's like shaped like this, and it's comes up to a high point. Wait, here. Doing this on my computer is hard. And we have watched, now pretend my hands are still here. We have watched from satellite their production wells going from the edge of the field up to the top of the field, which can only happen as the field is depleted. You see, the oil, remember the oil and gas and water interface. The oil is moving, the remaining oil is a thinner and thinner layer nearer and nearer the top. And so we watched the production wells go up this anticline to the top. And we know that is only, and we watch the original wells out at the edge being turned off. Why? Because there's no oil there anymore. They're pumping water. And so we know that the numbers that they give year after year, the same numbers have to be false. But Saudi Arabia likes to say, we're the biggest oil reserves in the world, and you better do what we say. And other countries were like that too. Now, another thing happened to exacerbate this. This is still part of my number one reason. And the OPEC allowed countries to pump in proportion to their reserves. And all countries need more and more money for the same reasons all governments need more and more money. And so what each OPEC country, OPEC, Organization of Petroleum Export Countries, what each of them wanted to do was to make it look like their reserves were as large as possible so that they could pump more oil. So, okay. Jean Larrière, my colleague, and Roger also thinks that they are inflating their numbers so that they can pump more oil. So in about 1988, all of the estimates from all of the OPEC countries jumped up. As one wag said, without a single bit being put in the ground, an oil bit into the ground. And they're doing that to increase their numbers, although so they could pump more. Okay, that's reason number one. Reason number two is you drill down, you find an oil field, and usually for tax purposes, you underestimate how much oil that is there. Oh, it's only 100 barrels. But over time, as you discover what are called extensions and new fields and new pools and old fields, little offshoots, the amount of oil that you get from that original strike is increased by about a factor of 8, roughly. Now, what's happening, and let's see if I can find this in my PowerPoint here. Just a second, folks. I'm going to zoom back. Here. Here. So they are adding the revisions and extensions, they meaning the official estimates, are adding the revisions and extensions into that year's new oil, when in fact you should attribute them to the year in which the well was found. So that difference is the largest reason that the brown line, the official estimates of how much oil remains, is compared to the green line, which is our estimate, which meant we backdate the revision extensions to the year in which that oil field was found. And I don't know if you consider that arcane or you understand the logic of what we're doing. But whether you take let's just say the extension, the field is bigger than we originally reported. That's an extension. And we reported it in 2020, but we actually found the field in 2010. Should you take this new oil, and should we attribute it to 2020? We think no. Or 2010? We think yes.
So
Okay.
the brown line should have been higher 10, 20, 30, 40 years ago
Yes,
and more level now.
yes. The area under the curves are the same, more or less. The areas under the curves are the same. Now, see this jump here? This is when OPEC was fighting for quotas. And this is simply adding, they're called speculative resources by Jean Larrey. And this very good Arab oil analyst, Al Husseini, I mean, we think he's really good. He said, well, look, this is what's going on. Those guys are just upping the reserves on paper so they can pump more oil. And this is all, there's a lot of literature on this. And here we included tar sands for Canada and Venezuela. Well, that's not oil. You know, it's overcooked oil. But we can turn it into something you can put it in your car. So maybe we should include it, even though it's very very difficult to get. So that's a good question, Clark, and that's my answer. There are two reasons: overestimates, and whether you put the revisions and extensions into the year that you found the oil field, or into which the year they were officially added to the inventories. And oil companies don't like to do that because then they get taxed on their oil.
Well, thank you. That's helpful.
Okay.
Hey,
Do
Charles,
we have any other questions? Carl?
can you hear me?
Yes?
Oh, good. My microphone's working now. This chart is a very useful chart. And there are two way approaching it as an economist. There's such a thing as economic reserves as opposed to actual physical reserves.
Yes.
And economic reserves are what is economical to produce. So as the oil price goes up,
At the technology of that day.
at the technology of that day, that's correct. So as the price goes up, I would assume that this chart might change if, say, oil was at $300 a barrel. Would that be correct or no?
The short answer is yes, and let me think for a minute. Carl's question is a very sophisticated one, and one of the better ones that are used by economists against me. And I'm not saying Carl is doing that. I mean, Carl is asking a good question. What kind of economist are you, Carl?
Actually, an energy economist. I worked in the energy business for a long time. So,
Oh my, this should be
but I
interesting.
am one of those economists that's highly sympathetic to the limits to growth
Okay,
thesis.
good.
And my real question gets to the idea of adding to the cost of energy, this what economists call the social cost of carbon. I don't know if you're familiar with that idea
Oh,
or
sure.
not.
Sure, I've written on it.
And so, for example, tar sands up above here would come way down in terms of economic reserves because so much of tar sands requires the combustion of those uh, rocks, basically, to heat them up to get the some of the oil out of those rocks, and so they're generating a lot of carbon emissions in the course of producing the usable oil. And if you factored that in, um, the externality cost of aggravating the whole emissions and carbon change, global climate change phenomenon, so much of that and so much of other oil would not be economically viable to extract.
Oh, I have an interesting answer for you, one you will not predict. But first, let me answer the first one. The energy return on investment, I mean, you can imagine that at $300 of oil, of course, we're going to produce more oil, or we're going to produce crappier oil from poorer resources increasingly over time. And we've written about that too. But if until the point where a barrel of oil produces only 1 barrel of oil, the EROI is 1 for 1. At that point, I think it has to be non-economic unless you want to take coal and burn 2 joules of coal to make 1 joule of oil. I suppose you could do that. Maybe we will someday. I think about these things because when it gets tough going, we're probably going to burn all kinds of stuff. I had a friend who was chief forester for Argentina, and he said that they had Europeans, this was 20 years ago, crawling all over Argentina looking for every stick of biomass they could to take back to Europe and burn it. And, you know, they, at that point, whatever the situation was, 2008 or something, they were getting pretty desperate for getting something to burn. Until, you know, then they got gas from Russia and it relaxed for a while. Okay, what difference will it make when the price goes up? Well, the energy return on investment is so low now, about 10 to 1 on average, for most places in the field, except maybe the Middle East, that I don't think increasing the price is going to increase the ultimate extraction very much. I'm going to have to think about that a little bit more. But I don't think it's going to increase it very much because we're already so low, and increasing the price, well, it might transfer wealth, but it's not going to be a net addition to society if we're using a barrel of oil. Well, it's like, except for the subsidies, it's like ethanol today. We put ethanol, 10% of the whatever we put into our gas tanks is ethanol, even though it's an energy deficit, or break even at best. So in other words, it takes a joule of fossil fuel to make a joule of ethanol you put in your car, probably more than a joule. But we do it because we're subsidizing it. We have an official government subsidy that subsidizes the farmers. And I drove across the middle of the country a couple of years ago, and it depressed the hell out of me because the whole landscape was just cornfields and retorts to refine it, to distill it, and storage tanks. The whole middle of the country was given over to making growing corn, of which we ate only 5 or 10% of it and gave half the rest to animals and half the rest to our gas tanks at no energy gain. And hardly a stick for a bird to sit on was left intact. And then every town had these enormous petroleum distribution centers for the petroleum, the diesel for the tractors and the transport systems, and gas for the drying and so forth. So it depressed the heck out of me. So yes, something like that will happen. If the price of oil goes up to $300 a barrel, we will pull the oil out of the ground faster. I don't think we will get any more. Not much more, maybe a very little. Now, the second, what was yours? Oh, the second question. You know, Carl, if you're an economist, why are you only dealing with costs? Shouldn't you be dealing with cost benefits? Isn't that what economists do?
Right, exactly.
Okay, well, I figured out the benefit of burning a barrel of petroleum. They said they want to have a tax of $100 for the environmental impact. That's fine with me, I guess. But what's the benefit of burning a barrel of oil? Well, I'll tell you what it is, about $10,000 worth of GDP,
Yeah, right.
right? So no way in hell are we gonna worry about that. People burn oil because it produces wealth and everybody wants wealth. How's that?
Right, but economists like good accounting,
Yes,
and they like the most more modern economists like to account for the externalities. And so what they would say is people would demand less if they paid a price that reflected all the costs. Uh,
supposedly.
and so some economists now think that the social cost of carbon is over $200 per metric ton of coal equivalent.
Yeah.
Is that right? Metric tons of CO2, I'm sorry.
CO2
Uh, and so if everybody paid that, that would mean something like $25 per gallon of gasoline being taxed.
and our economy would collapse.
And partly because a lot of the so-called wealth that you referred to is actually fallacious. We're not doing our accounting correctly. We burn so much gasoline and so much air kerosene, airline fuel, and without realizing the damage we are causing. And so we think we're creating wealth and creating value because we can zip around the world in all these wonderful cars and planes, but in fact, it's not wealth at all. We are nails, hammering nails into the coffin of future
Well,
generations is what we're
it's what
doing.
it's wealth. It's wealth to me. I just went camping up at Silver Falls. I just drove up there in my camper and went camping
But
and
would
got
you have
rained on for 4 days.
but
But
would
I
you have
drove.
camped? Would you have camped if you paid $25 per gallon of
No,
gasoline?
but we don't pay it. It's our children and grandchildren who pay it.
Right. I know it's an intergenerational transfer. You are experiencing wealth at the expense of the poverty that will be experienced by future generations. So that's what
Not
I'm
my
saying.
descendants, Carl. Not my descendants. I have none. They're
Oh,
liberal.
well, you've got nieces and nephews probably that you
Yeah,
might be a
yeah,
little bit concerned about.
but they
But
haven't
no,
reached.
that's all I'm saying is we think we are wealthy, but a lot of that perception of wealth, because it's at the expense of future generations, is fallacious.
Well, Carl,
And
tell me what you think is going to be worse. The environmental impacts in, say, 30 years, the environmental impacts or the lack of oil. Which do you think is going to impart your grandchildren the most?
yeah, that's well, after hearing your lecture, I have to say, it bef an hour ago before I heard your lecture, I would have said the environmental impacts would have been greater. Now I'm not so sure. Maybe we'll run out of oil before the sea level goes up enough to for us to be even more alarmed about that. I don't know. What do you think?
Um, well, it's a guess. I mean, it's a close horse race. But I think that society in general will be more impacted by the loss of what I call premium fossil fuels, and that's oil and natural gas liquids, than by climate change. The I have some issues with climate change too, but I think it's a huge potential problem. Sea level rise and so forth. I just wrote a paper called "The Perfect Storm" of all these things coming together. They're going to come together. So if you want to write me, chall@esf.edu, I will send you my perfect storm paper, and you can see what do I think is worse. They're all going to happen at once. And,
Yes, that's an
and,
interesting
and
thesis.
we'll think, these wars in other parts of the world, we just won't care because we'll be, and we have all kinds of other things that the sunspots, if we have a big eruption like what it was, a Pennington or something sunspot in 1870, and all the telegraph offices burned and caught fire, and electric shocks when shock leaping out of the telegraphs. There's all kinds of possible things. But the one I have some ability to predict, and I think pretty good ability, is we're going to be flat out of the best stuff, oil, for economic activity. And this other, I cannot imagine that wind turbines and solar rooftops are going to fill in for the oil. I mean, even now they are at most what are they, at most 10% of electricity, and electricity is only 20% of all the energy we use. So just driving on Route 5 and looking at all those trucks bringing us food from California and stuff, how are you going to do that without diesel? I have a colleague, she's great, and she wrote a book called "When Trucks Stop Running." And it's a great book. Look it up, "When Trucks Stop Running." And what does the world mean then? So, Clark, I think there's just all kinds of economic questions that are not answered by marginal transactions in the marketplace. And I'm going to talk about that in my next few lectures, by the way. The next one you can fault me on, probably. I would certainly hope you're going to be there to correct any misrepresentations you think I make, because I'm going to tell what conventional economics does, and then I'm going to criticize it.
Well, thank you. I kind of consider the economy, the global economy, to be a little bit like riding a bicycle. A normal bicycle stays vertical on two wheels because we're able to turn the wheel in such a way that you've got
Negative feedback.
that constant feedback, right? Now imagine a bicycle where when you turn the handlebar, the wheel responds only 5 seconds later.
Yep.
Now and so it's the lag between the decisions we make today with the information we have today and the consequence of those decisions that are delayed maybe 5, 10, 20 years in the future. We're like riding a bicycle whose handlebars have a lag between the turn and of the handlebar and the turn of the wheel. And we're stumbling as a result. It used to be in economics, today's price would result in a change in today's demand. And supply and demand worked because they were always happening concurrently. But when you deal with the environment, you're dealing with a system that responds only after a lag. And we're not aware of that. And so equilibrium will always be elusive because of that.
Well, these are good remarks because at one time in my graduate student life, I studied systems dynamics, and all the things you talk about were very much talked about in general, in design of airplanes and all these kind. I mean, you just imagine what designing an airplane where you had a delay between what when you got some information and your ability to respond to it.
Yeah, yeah.
In fact, I think there were two recent Boeing crashes that were
Yes.
just exactly that. And yes, I think we are doing that in our society. Well, my official time is up. Is there anybody else who would like to ask me a question? I didn't get to limits to growth. I suppose I will start with that next time because we certainly want to cover that. And anybody else want to say anything? Good discussion.
Only thank you for a very illuminating lecture. That was great.
Thank you very much. Thank you. I don't know. I don't get a lot of feedback here, but a couple of people have given me very nice feedback. So for some
I'd
of
like
us,
to I'll send you my email address for the paper you mentioned.
okay, which one?
Oh, the perfect storm.
Oh, yes, okay. Yes, chall@esf.edu, although I guess you have it.
Yes, thank
And
you.
just write perfect storm. Okay?
Okay.
Like this oil paper you discussed today?
Oh, that would be a bonus. Sure, I'd love that.
I mean, I can drown you in papers if you want. That's
Well, the studies you've done of the energy flows in ecological systems is also fascinating. I just think that's a whole fascinating topic.
well, I'll just
You could
write.
teach you could teach an Ollie course just on that, I think. I
Oh
mean,
yeah.
that is just a fascinating
That was
topic.
my bread and butter for years. I taught systems ecology, ecosystems, regular. I in an environmental course for freshmen. That was a lot of fun too. So
Yeah.
that's how I made my bread and butter over all the years. Nobody ever paid me to work on energy. Nobody pays anybody to work intelligently on energy.
And I don't know if academics have been studying this aspect, but if you've got a whole complex ecology modeled in terms of the interaction between species and the energy flows and so forth, what happens when you pull a lot of biomass out of that system? What happens like from fishing, for example, or any kind of commercial extraction from that ecosystem? What happens to the other species and what happens to the whole ecosystem?
Well, we know a lot of case histories of what happens. So we catch sharks. And no, a better example, well, you might know this if when we harvested sea otters, the urchins grew and they ate the kelp and destroyed the whole kelp coastal ecosystems that were supporting all kinds of fish. So, we have many such examples. They caught all the cod down in the Atlantic, even though the production of cod, the catch of cod was becoming very high. The fisheries scientists said, but they're smaller. You're taking out next year's fish this year. And so the fishermen compensated for that by illegally putting in smaller mesh in their nets so they could catch smaller cod, and they kept the fishery going up until 1970, I think it was. Looked like the fishery was better and better and better. And then it absolutely went to close to zero. Just like that. So we have lots and lots of examples. Yeah, we
Well,
sort of know how.
yeah, that's overfishing of the cod, but what happens to some of the other species that interacted with the cod? They probably went down too. In other words, cod was part of a
Well, I
larger
would guess,
ecosystem.
I haven't heard it, but one would imagine that pollock and haddock, which are competitors, would have increased. But I don't have any information that that took place.
Yeah, yeah.
I don't know. Lobsters, on the other hand, we fished lobsters harder and harder, and the lobsters actually kept kept growing. I don't know if it's true still, but and what the lobsters were doing is they learned how to crawl into the lobster pots and eat the bait, the fish that they put
And then
in there.
climb out.
Climb out. And they didn't have any idea that until they put a camera down there on the lobster pot, and you see the lobsters just knew just how to come in and out. And it was just an accident that they were in the pot when it was pulled.
Well, so in 1974, when the Magnuson Act was passed, or 73, I can't remember exactly, all these fisheries were supposed to be managed rationally
Ah.
for long-term benefit and to sustain those fisheries. And
Well, maximum sustainable yield, and that was a joke too.
yes, so it sounds like I haven't been following uh, the results of this paradigm of regulation of the fisheries, but it sounds like it has not been successful. The fishermen were supposed to be playing a role in regulating themselves uh, for their own long-term benefit, and it sounds like that has not worked. And if it hasn't worked for fisheries, how is it going to work for any other aspect of the environment? If people can't regulate an ecosystem for their own rational long-term economic benefit, what what does that say about the future of any kind of, you know, uh, regulation that involves influence by stakeholders who are,
This is
yeah,
what happens. The fishermen, times are good, fish are plentiful, and they buy boats, and they're very expensive, and they have to pay them off over 20 years,
yeah,
which means you got to keep the fish coming in, a lot of them,
right,
and that ultimately ends up with them being overfished. So, I mean,
yeah.
look at our own local fish. It's a disaster. What we've done to steelhead and to salmon locally is a disaster.
So the financing of the boats long term runs exactly contrary to the necessity for better, more
Better
responsive
management for the
regulation.
fishermen. Yep.
Yeah, yeah.
Well, that's one. It's a
So
complicated.
this is another example where we have let things become subordinate to the imperatives of Wall Street and the financiers.
It's
And if
part of the whole concept of industrialization that getting your livelihood requires more and bigger machinery, like farmers or dairy farmers today. And,
yeah,
you know, I just read something. My wife has been buying this Alexandra supposedly benevolently raised milk products. And we just got this report in about all these inhumane things that take place on their farms. At least it's reported, everything is, painted green, painted, whether it is or isn't. And what we're doing is just exploiting nature and animals and everything else. And then the implications of those are hidden from us because nobody wants to hear it.
Right. So if the National Academy of Sciences announces we all have to stop using fossil fuels tomorrow, uh, we won't be able to do it because we've got long-term debts to repay to Wall Street. So we have to let the planet.
It's like we've invested in our boats.
We've invested in our boats. We have to repay our debts. We can't stop now. So we'll have to destroy the planet. So I don't get that whole paradigm has got to be supplanted by something new.
Oh, Eric, you've got lots of solutions, don't you? That's
But
a
I
joke
think you can
because Eric
see,
is.
I think so much now depends on the buy now, pay later way of life that we have succumbed to for decades. And this is, the massive amounts of debt that our society has accumulated really limits our ability to make choices for the future, unfortunately.
I think that's a pretty good insight, Carl. Unfortunately, our economist is left, but you can try it on him next time.
Well, we are in some ways, you can see the way we treat the planet and ecosystems as a part of as a symptom of global economic liquidation. It's like,
Well, the original hunter-gatherers that were on this continent, they were responsible apparently for the extinction of all kinds of what are called megafauna, large animals, everywhere in the world. So humans, I mean, I suppose maybe that the lion would, if he could, overexploit his gazelles. Um, I don't know that it's just humans, but humans, certainly we knew that humans have done it. They didn't start 200 years ago. They've been doing it. We've just become more powerful at doing it.
yeah. Well, Bill McKibben wrote this book. It was one of his most famous ones, I guess, one of his early ones also, called The End of Nature.
Oh, yeah.
And one of the I think the first chapter, he talks about uh, if he encountered the last two species of a beautiful bird,
Yeah.
the last mating pair, and his son was starving and needed
Yeah.
food, he would kill that last mating pair to feed his son. And it's a sign of the predicament the human race is in.
You got it,
That
Carl, but I got to go.
Oh,
So,
okay.
yeah.